Well, good day to all of you. So, before I proceed further, we have already learnt the criteria for confinement and how, and rather the dimensionless groups or the dimensional numbers which define a microchannel. Now, I would just like to be a little more systematic and first discuss the different important dimensionless groups which are important for microchannel flows. Now, when we talk about any flow system, flow of water through a pipe, whatever we talk about, the first dimensionless group which comes to our mind is the Reynolds number, right. What is Reynolds number? As all of us know, it is basically the inertial force, the ratio of inertial force and viscous forces. Usually we define it in terms of some particular average or characteristic dimension, some particular average or characteristic length and the fluid properties. This has been very important in single phase flows, primarily because it gives us a criteria of transition between the laminar and the turbulent flow pattern, we know it. So, therefore, whenever we talk of multiphase flows, whenever we talk of single phase flows, Reynolds number is the first dimensionless group which comes to our mind. Now, let us see whether the Reynolds number is equally important for this particular case, or in other words, what are the other numbers which come into picture for microchannel flows. Now, whenever we are talking about microchannel, the most important force which comes into being can be said as capillarity or the surface tension forces. And viscous effects with or against, it should be against capillarity. Well, from these particular balances should evolve the relevant dimensionless groups for two phase microchannel flow, isn't it? So, this is something very logical that in macro systems inertial force and viscous forces are important. So, naturally Reynolds number came up as a consequence. Whenever we are going to the micro scale, naturally we have been discussing, you have been bored by hearing that surface forces become important as compared to gravitational forces, etc., etc. So, naturally surface tension forces should be dominating here, and therefore, other forces they should be balanced against the surface tension forces, and only from those balances we should be getting a proper representation of the different dimensionless groups. Also, we have come to know that rather in the last to last discussions, we have also come to know that in microchannels the major flow pattern is the plug flow pattern. Then under very high gas velocity we come across the annular flow pattern. Now, in annular flow pattern what we have seen, there is a gas core and a thin liquid film, and in plug flow there are short plugs which occupy the entire characteristic dimension, right. So, therefore, keeping this in mind and balancing the different forces, we come across the different dimensionless groups which should be pertinent for microchannel flows. Now, suppose we balance capillary against say the gravitational effects, then in that case what do we get? Maybe suppose we balance your capillarity with gravitational effects. We have already come across this particular number which we call as the bond number, and this is actually defined as rho g L square by sigma, where this particular L, this is a characteristic dimension, For most of the cases, it is the tube dimension or a conduit dimension, and this gives us the ratio of gravitational to surface tension effects on a liquid surface, right. So, from here we can know that when gravity will be dominating over surface tension and vice versa. Now, from here it is very evident that a low Bond's number can be attained either by reducing G or by either by reducing by increasing sigma or by reducing G. So, therefore, low or rather small bond number systems can be achieved either under microgravity conditions or by decreasing the channel length. For example, the situation which happens under capillary tubes. So, therefore, usually the characteristic length is defined such that under normal gravity conditions bond number is less than 1. This is the primary group for microchannel flow. So, therefore, this can be achieved, as I have already said, under microgravity condition or for very low dimensions for normal gravity condition. And so, whenever till now you have seen, whenever we were defining a microchannel, it was on the basis of bond number. But if you observe the particular expression, you will find that it is applicable for a stationary or a static system. It does not have any velocity component in it. So, therefore, although it can define microchannel flow, but it does not say anything about the flow characteristics in a microchannel. For that, we need to introduce the inertial term or we need to have some particular velocity term. So, for achieving that, the most commonly used number is which discusses the relative importance of capillarity and viscosity. This is the most pertinent viscous forces. This is the most pertinent non-dimensional group in flow systems, and this is known as the capillary number, defined as mu liquid U by sigma, where U is some particular characteristic or average velocity or characteristic velocity of the system. So, we find that more or less when we have a small bond number much less than 1 and your capillary number greater than 0.1, for what happens? Significant distortion of gas liquid interface occurs, right? Why? Due to viscous stresses, isn't it? So, we find that when bond number is for low bond number systems only, suppose capillary number is much greater than 0.1, then only it is naturally that shows that viscous effects are much more important, and since viscous effects are much more important, it is quite natural that the gas liquid interface, the sufficient distortion occurs due to this particular reason. Now, this was by balancing capillarity and viscous forces. The next thing which we can do is we can balance, or we should be balancing, capillarity with inertial forces. What does this give us in this particular situation? We find this gives us a number as rho L u square by sigma, which can be defined as the Weber number. I do not know whether you are familiar with this number or not. This gives a measure of inertial effects to capillarity effects. Again, for small bond number systems, when bond number is much less than 1, we find that when Weber number is high, what should happen? Inertial forces should dominate and a liquid surface should break up, isn't it? So, for small bond number systems, a liquid surface breaks up due to inertia if Weber is greater than 1. So, while capillary number, it showed us that significant distortion of gas liquid interface occurs due to viscous stresses, or in other words, good amount of waviness sets in. On the same time, Weber number tells us that the liquid surface will break up due to inertia if Weber number is high. Well, so these were the important numbers. If you observe here, the Weber number, the capillary number and the Yodvorst number, which are useful for microchannel flows. Now, if you observe the Reynolds number, which I had already written down here, you find that in the Reynolds number part, we have the inertial forces as well as the viscous forces. Now, we observe that the Reynolds number, it does not give a very good representation of the flow in microchannels. The primary reason being the length parameter and the average velocity parameter that we select to define Reynolds number, they are not very appropriate for microchannel flows. On the other hand, there is another number which is known as the Suratman number. This particular number, Suratman number, sorry, it is not num, it is, I will write it properly, it is Suratman number. Now, this number you find that this is a very interesting number. This number is basically defined as rho sigma L by mu square. This is actually, it can be referred as measure of surface tension forces compared to inertia inertial forces when velocity scales as a balance between surface tension and viscous drag. What does it mean? In other words, it means that in the Reynolds number, if we replace the characteristic velocity of Reynolds number with sigma by mu, then we get this particular Suratman number. So, therefore, the thing which I was telling, that Reynolds number is not appropriate for two-phase flow in microchannels, primarily because it does not capture the physics of flow in this microchannel system. This is because the characteristic length and the average velocity which we select for defining Reynolds number are not suitable for microchannel flows. On the other hand, if the velocity is replaced by the velocity in the capillary number, that is, if it is replaced by sigma by mu, then we find that this Suratman number, this gives us a much better representation of flow characteristics in microchannel flows. And if you observe the number, you find this is nothing but Reynolds number square into Weber number. So, therefore, this gives a very good idea about the measure of surface tension force compared to inertial force when the viscosity is defined as a scaling parameter between surface tension and viscous drag. So, it is nothing, it is basically the Reynolds number defined with a proper characteristic velocity. Now, if you observe this number very well, what do you observe? You observe that the number, the Suratman number, it gives a measure of degree of damping in a two-phase flow system for a two-phase flow low bond number system. Is it clear to you? So, what we find is that this particular Suratman number, it has got several particular physical interpretations. One is the number, the physical significance, then it is basically Reynolds number with u replaced by sigma by mu. Thirdly, it is Re square into Weber number, and in general it gives us a measure of the degree of damping in a two-phase system, provided it is operating at low bond number. So, for low bond number systems, what do we find? That if two-phase flow occurs in a straight pipe, right, for two-phase flow in straight pipes, at low bond number, we find that rapid changes in gas liquid configurations take place, or rather flow patterns they keep on changing. And what happens? We find that at high Suratman number, slug bubbly transition takes place, isn't it? And at low Suratman number, your slug annular transition takes place. Why? Because we find that at your high Suratman number and low bonds number, what happens? The pinching effect it forms. Okay. So, when we have low Suratman number, it means that viscous forces are important, and as a result of which we find that in under this particular condition, the annular flow, it breaks down to form slug flow. So, therefore, one particular range of Suratman number should define the range of existence of the slug flow pattern. If the number is higher than that, then the slug bubbles, they break off to, or rather the liquid inertia is sufficient to break off the slug bubbles into smaller bubbles and form bubbly flow. And if the number is below any particular critical number, then under that condition viscous forces, they start dominating, and the annular flow is formed with a continuous gas core and continuous gas core and an annular liquid film. Okay. So, therefore, we find that just like Reynolds number was so very important in macro scale flows, Suratman number almost assumes an equal importance for microchannel flows. Now, after this, we would just like to see initially what we did. In the first place, we defined, or rather we discussed the importance of microchannel flow. We discussed the specialties of the different flow patterns which occur in microchannel vis-a-vis macrochannel flow. Now, there are two aspects we should remember. First thing is, we should know what is the distribution. Just like in in single phase flow, we should know what are the distributions. We know that the distributions can be either laminar or it can be turbulent. If the distribution is laminar, we would be using the relationship of friction factor as F equals to 16 by Re if it is Fanning's friction factor, or 64 by Re if it is Darcy friction factor. And suppose the flow is turbulent, we have a large number of equations, any of them we can use. And next thing is, when should we use Fitch equation, or in other words, when will the flow be laminar? If the flow is laminar, what is the equation we know, but when will the flow be laminar and when will the flow be turbulent? Or in other words, what is the critical Reynolds number to identify the transition between the two? We usually depict this as Moody's plot, which plots F versus Re. Now, similarly in two-phase flow, it is very important to know what are the different distributions. Along with that, it is very important to know when each distribution exists, so that we can know that when the flow conditions are so and so, so and so, we would expect this particular flow pattern, and accordingly some specific void fraction and pressure drop model is going to be applicable for that case. Now, in order to identify the range of existence of the different flow patterns, usually two-dimensional plots are adopted. These plots with suitable coordinates, they identify or they divide a two-dimensional area into different regions where each and every flow pattern exists. One of the oldest flow patterns for gas-liquid upflow in vertical tubes plots the flow patterns in a two-dimensional plot with superficial momentum flux of the gas and the liquid phase as the axis, and naturally they show that at high momentum flux of the liquid, bubbly flow exists, at high momentum flux of the gas, the annular flow exists. Similarly, the oldest flow pattern map for horizontal pipes was proposed first by Baker, and then it was obviously much more modified, and that also gives us the rather divides the entire two-dimensional plot into areas demarcating different flow patterns using two different axes, which considers the mass flow rate of the gas and the liquid along with dimensionless groups defined in terms of the properties of the two phases. Now, if we go through literature, we find that people have again lot of confusions regarding the most appropriate dimensionless group to be used for defining flow patterns. This is quite obvious because we find that when the transition occurs between different flow patterns, there is no one mechanism which governs the bubbly slug, slug churn, churn annular, all the transition mechanisms. For example, bubbly slug occurs when the coalescence between the bubbles is so high that they form the elongated Taylor bubble. So, naturally in this particular case, your bubble coalescence should be the dominant phenomena. On the other hand, if we observe slug churn transition, what do we find? We find in the Taylor bubble region there is a downward flowing liquid film and an upward flowing Taylor bubble. So, therefore, there is counter current flow in this particular region, and of course, there is a liquid slug which flows upward. In churn flow, we find that the whole system becomes chaotic. The counter current flow is no longer maintained. So, people have postulated that possibly flooding is the mechanism of transition. And again from churn flow, if you go to annular, what do you find? Both the gas core and the liquid film are flowing in the upward direction, which shows that initially flooding had occurred and now flow reversal has occurred. So, naturally it is quite evident that bubble coalescence, flooding, flow reversal, all of them cannot be predicted by the same physical mechanisms, or the same dimensionless or dimensional numbers cannot be used to bring about all the transitions together. That explains the confusion in selecting the axis of the different flow pattern maps, and as a result of which we find that a large number of coordinate axes have been adopted for vertical as well as for horizontal flow pattern maps. And in this entire confusion, what people have finally decided is that the superficial or the inlet velocities of the two phases are the best coordinate maps, or in other words, they are the most popular axis. So, accordingly, we find that a large number of flow pattern maps have been predicted with the gas and the liquid superficial velocities. This is one typical map for horizontal gas liquid flow. As expected, as low gas and low liquid we have stratified, then at high liquid we have dispersed, at high gas we have annular. So, it simply has divided the entire two-dimensional region into some areas dominated by different flow patterns. Now, in the next class we will be discussing the relevant flow pattern maps for microchannels and how are they represented, what are the problems of these particular flow pattern maps, and finally we will be discussing an analytical model based on basic physics which governs the transition criteria in microchannels. Thank you very much.